Launching a containerized application into a production environment carries a distinct operational vulnerability. If the isolated process halts, the application goes offline. Docker operates on an imperative execution model. An engineer issues a run command, the engine spawns a process, and its job is essentially complete. There is no continuous oversight of that application's health. In this diagram, a standard container deployment functions as a linear path. When the container fails, the system simply stops. Restoring service requires manual human intervention to identify the crash and execute a new start command. Relying on a human operator to notice downtime and manually restart failed components creates unacceptable latency. Without intervention, a crashed container remains dead. Kubernetes functions as a dedicated orchestration engine to address this gap. It achieves this through a declarative loop known as reconciliation. Instead of instructing the system how to run a process, an engineer declares the desired state, specifying that one web server must always be active. The system then continuously compares reality to that declaration. Here, the reconciliation loop detects the discrepancy between the crashed reality and the desired state. It automatically terminates the failed process and replaces it with a healthy instance, completely bypassing the human operator. Transitioning to Kubernetes means shifting from manually executing workloads to guaranteeing their uptime through continuous automation. This automation relies on a strict architectural division of labor between management logic and application execution. This diagram illustrates the structural split. The cluster is divided into the master node on the left and the worker node on the right. The master node functions as the central intelligence of the cluster. It schedules deployments, tracks system state, and processes all API communications. Inside the master node, 4 specific components drive this intelligence: the API server to process external requests, etcd to store cluster data, the scheduler to assign workloads, and the controller manager to enforce the desired state. The application workloads execute on the worker node. This is the hardware environment equipped with the CPU, RAM, and storage required to run code. To receive instructions from the master node, the worker node relies on local agents, specifically the kubelet and the kube proxy. Kubernetes does not interact directly with raw containers. The system operates using its own logical unit of administration, called a pod. The pod wraps tightly around the container. Kubernetes schedules and monitors the pod, while the pod itself manages the lifecycle of the containerized application inside. This distinct separation allows the master node to manage thousands of individual pods across a fleet of workers, without the management logic becoming entangled with the application code itself. Engineers communicate their deployment requirements to the cluster using a client binary called kubectl. When a user initiates a deployment, the command is transmitted directly into the API server on the master node. The API server acts as the system's gatekeeper. It authenticates the incoming request and translates the user's command into a recognizable system resource. That requirement must be stored. Kubernetes uses etcd, a highly available key-value database, as the ultimate source of truth for the entire cluster. The API server records the requirement into etcd. The desired state is now registered. Registration alone does not execute the code. The active engine that drives deployment is the controller manager. The controller establishes a continuous loop connecting the database to the worker nodes. This loop constantly compares the current state executing on the worker node against the desired state stored in etcd. If a fatal error causes an application to crash, the current state diverges from the desired state. This mismatch triggers the automated self-healing sequence. The controller loop instantly detects the crashed pod. It instructs the kubelet to terminate the failing process and spawn a healthy replacement, restoring parity between the worker hardware and the database. High availability is achieved entirely through this API-driven automation. The reconciliation loop ensures continuous resilience without requiring manual intervention. Managing a single application is straightforward, but enterprise environments require hosting multiple distinct engineering teams simultaneously. These teams deploy independent services onto the exact same physical worker nodes. This diagram illustrates a crowded worker node. We have blue payment pods and green shipment pods, all drawing from a single shared pool of CPU and RAM. This setup creates the noisy neighbor problem. A sudden traffic spike to the payment service will demand massive amounts of processing power. If left ungoverned, the expanding payment applications consume the entire shared capacity. The shipment services are starved of compute resources and begin failing. Without boundaries to enforce fair resource distribution, a shared cluster is structurally unstable. To resolve this, Kubernetes implements an administrative segregation mechanism called namespaces. A namespace establishes a strict logical boundary. One isolates the payment team's assets, and another protects the shipment workloads. These boundaries exist entirely within the API logic. The underlying server hardware remains shared, but the access and visibility are segmented. Crucially, namespaces enable resource accounting. Administrators apply strict CPU and RAM quotas to each boundary, capping the maximum compute power a single namespace can draw. Once these allocations are enforced, the runaway payment service is constrained by its quota. The shipment pods regain their required processing power, and stability is restored to the cluster. Namespaces provide an essential governance layer. They transform chaotic computing environments into secure platforms capable of safely hosting multiple independent engineering teams. Operating isolated containers is vastly different from managing a governed Kubernetes architecture. This visual shows a standard deployment command. By appending a namespace flag to the query, engineers target specific administrative boundaries. This filtering mechanism eliminates the noise of thousands of unrelated applications, simplifying observability so developers monitor only the data relevant to their exact scope. In the background, the master node's reconciliation loop continuously monitors that scoped environment, protecting the desired state against inevitable hardware failures. The namespaces provide the risk management and accountability required to ensure no single application can monopolize the system's hardware. Looking at the entire architecture, the API server routes traffic precisely into these governed boundaries, while the controller rhythmically maintains the health of the pods within them. This specific combination of continuous automation and strict resource governance forms the core of modern platform engineering. Kubernetes establishes an automated, mathematically guaranteed administrative order for cloud-native infrastructure.